This video is to go over lesson 1.11, and let's go over problem 8. It says tennis balls are sold in can of 3. Which is greater, the height of the can or the circumference of it? So let's say we have 3 tennis ball, and which one will be greater? Is the height of this can greater than the circumference of this can? Yeah, that's the question. So which one will be longer? That from here to here or this? Think about this, how you get the circumference, and think about the heights of this. You can just simply say the height diameter of this tennis ball. You have to think about that. The diameter of tennis ball will be, I don't know, it can be whatever. Let's just say 3 inches, for example. Then what would be the height? If the diameter is 3 inches, then what would be the circumference of it? That circumference, I want you to notice that will be the same as the circumference of the fattest part of the tennis ball. Problem number 9. In the figure below, line CD is parallel to line AB. So we've got that line CD. CD is parallel to AB. How can you construct a right triangle that has the same area as EFG? So we've got whatever the triangle EFG, and if this triangle is right triangle, meaning that you have 90 degrees right there, what would be the area of this? In order to find the area, no, it doesn't say that. How can you construct a right triangle that has the same area? So how can you make sure that that will be 90 degrees? Think about the geometry software. Problem number 10. Use geometry software to construct a rectangle, then divide the rectangle into a square and a smaller triangle. A. Find the length to width ratio in each rectangle. What do you notice about the two ratios? If you have geometry software at home, that's great, but if you don't have one, but if you have internet, you can go to GeoGebra. You can Google that, and you can get the geometry software, Geometry Sketchpad, like free online software, and you can try that problem. And the next one you don't need that. The figure at the right illustrates a special invariant ratio in geometry. Start with a particular rectangle, divide the rectangle into a square and a smaller rectangle. In the two rectangles, the length to width ratios are equal. In fact, you can divide the smaller rectangle into a square and even smaller rectangle. The length to width ratio to the smaller rectangle is the same as the length to width ratio of the first two rectangles. What's the numerical value of this ratio? So let's say we've got a rectangle L by X, and if you take square, which it has to be L and L, square, you have to have the same exact length, which is this, and this has to be the same. Then the length from here to here has to be X minus L, since from here to here is X and you're subtracting this part, so it has to be X minus L. And if you take a square right there, what will be the width length from here to here? It's got to be the same as this guy, right? So that's going to be there, and so on and so forth. Problem 11. says decide whether each ratio in parts A through C is constant. Even if you sketch the given figure, justify each answer. The square remains square. Is the ratio area of triangle divided by area of square invariant? If so, what's the ratio? So part A, let's say we have a square, and oops, not that way, this way. This way we have that. So let's say the width is x. If you don't like x, you can just simply say 4 inches or something, you know. Then if it's 4 inches, what will be the area of this triangle? Divided by area of square. If you're not comfortable with x, you can try 4 inches and you can get the numerical value. Area of square will be 16 because 4 times 4, and the area of triangle will be 4 times 4 divided by 2, so that's got to be 8, so that's a half. Change the value to like 4 to 3, for example, and then see if what you get out of it. Or maybe you can make it 2, or maybe you can make it 6 inches instead of 4 inches. Then as you do, you can start seeing a pattern. And basically this is what you can do for problem number 11. So next problem, you have the circle remains a circle. Then you take the radius and then you make a square out of it. What will be the ratio of area of a circle divided by area of square? So again, you can use numerical value first. So for example, if the radius is, let's say, 3, then the area of a square will be 3 times 3, which is 9. And the area of pi will be pi times r square. So that's 9 pi. Okay, let's keep the pi as it is, and we can simply divide 9 by 9. So the ratio will be pi. If you change that 3 into something else like 4, 5, or 6, what would happen? And you can do that for C. You can apply that to C. Problem 12. Maya constructed the regular hexagon inside a circle. So you've got the circle, and you've got 6 equal parts, and make a hexagon. That's the first part of the question. That's the center of the circle. The hexagon consists of 6 equilateral triangles. In other words, if you just that should be equilateral triangle. That's another one. 3, 8, 4, 5, and 6. That's 6 equilateral triangles. To compute the sum of the measure of the angles of the regular hexagon, she found the sum of the measure of the angles of the 6 triangles. From the sum, she subtracted the measure of each angle with the vertex at the center of the circle. What's the sum of the measure? So she added, she knows that this plus this plus this is 180. So she added these, these should be the same. So all the triangles together, right? So you see these dots. So this is 180. This is 180, then this is 180, and this is 180. I forgot that right there. So she added all together, all of these dots together, and then she subtracted the one inside. And what would be the sum? That's problem number 12. And this is the end of lesson 111.